Alright, so we've started talking here about volume using integrals. And so we spent some time looking at area and things like that, and so now we're going to look at volume. And so I've got a lot of this already written on here. So at any point you need to pause, go back, look at things, or hear things again. Just make sure you do that, and we'll see how this goes. I'm going to try to introduce a lot of this right now. Remember, if some of this stuff right here that doesn't make complete sense to you, it's okay. Just understand the process and how we get to it. So we're going to start by looking at what we refer to as a solid of revolution. So I've taken a function y equals x and I'm spinning it around the x-axis. And so when I do that, it creates a cone. And we're going to look at the volume of this cone from x equals 0 to x equals a, some arbitrary number. And so if you remember back with the area, we divided that area into rectangles. We're going to use that same process right now, but we're going to divide the cone into cylinders. And so you can see how I've already got this split up here. I've split it up into cylinders of the same width, and just like before, I can continue to decrease the width of those rectangles as much as I want. And so if you remember with the rectangles, we're going to let delta x be the width of the cylinder, or in this case it's really the height of the cylinder, the distance between bases. N would be the number of discs or cylinders that we have, and so we can multiply them together, and that gives us that a, that arbitrary value. And I can rewrite that, and remember there was a reason we want to rewrite that, and we'll do that again in this problem, so that delta x equals a divided by n. So then we think about, okay, how do you find the volume of a cylinder? The volume of a cylinder is pi r squared times the height. And so I'm going to go through and start finding the volume of all of these cylinders or discs added together. And so volume equals pi times delta x, that's my radius. It's how far it is from the x-axis up into it touches the blue line, squared, times delta x, because delta x is that distance right there. Delta x is the distance from base to base. And then it's plus pi times 2 delta x. Because 2 delta x, I have to go over 2 delta x's to go up to my spot on my function. Remember, my function is y equals x. So whatever my x is, my y value is, times that consistent height of delta x. And I do that over and over again until I get to my nth cylinder. And then remember, we have just a lot of rewriting and simplifying and factoring, and ultimately we get to a summation problem. And remember, we worked with a summation problem the other day. Remember, that summation can be rewritten, FOILed out, multiplied out. We can swap our denominators like we did before, so we have all of our n's over in one term, all of our constants in the other. Remember, this is a limit problem. We're evaluating it as n gets infinitely large or as our cylinders get infinitely small. And ultimately, we're going to get that down to a pretty simplified answer. The area is pi times a to the third over 3. And remember, since a is some x value, and in this problem x and y are the same, we ultimately get to a volume formula of pi times y to the third over 3. By all means, go back and look through this again, because I know it went pretty quick there at the end. So if you need to look through it again once or twice or whatever, or stop it at any point, make sure you do that. So what I've done here is I've found the volume of that cone. So as you go through there's two questions that you really should think about them. Two questions to think about, especially when looking at that end result. Okay, those two questions are, what integral would we have to use to get that answer? So what would be the calculus problem that we would have to use to get pi times y to the third over 3 as the answer? And then question 2, how does that compare to the original curve that we wrote down? How does that compare to the blue line, the y equals x? So think about that for a second. Maybe you push pause, maybe you think about what those answers would be. Alright, so what did you come up with? Anything? Well, the integral we would have to write would be pi times y squared. And I'll explain why it's dx in a little bit. And so then how does that compare to our original function? Well, that would be our original function squared and then multiplied by pi. I know this probably seems a little bit confusing, so let's just get to the rules. Let's see what it is, what kind of rules can we use to remember how to do this, and then we'll try some practice problems and see if it makes sense. So we'll kind of split this into two parts. If we are going to rotate our figure around the x-axis, okay, so we're rotating it kind of vertically, spinning it vertically around the x-axis, then our volume formula is going to be the integral from a to b of pi times y squared dx. And the reason that we have, and so a and b are our limits for our integral, and the reason we have it written like that is because you're going to write y as a function in terms of x. So it's not y you're plugging in there, but it's the function y equals something. That something is what's going to go in here. So for example, if y equals 2x plus 1, then we would write the function as the integral from a to b pi times, in parentheses, 2x plus 1 squared dx. So you can see all of your letters actually go with each other. They all agree with each other. Okay, so it's not y we're plugging in there, but we're plugging in whatever the function is for y. Now, if we're going to rotate it the other direction, if we're going to rotate it around the y-axis, alright, so we're kind of spinning it horizontally, if you will, alright, then it's going to be very similar. The volume formula is going to go from our two limits again, from a to b, okay, but it's pi times x squared dy. So again, just like before, we're going to be writing our function, whatever x equals in the problem. So our a and b are our limits, but now those limits are going to be y values now, not x values. And so we'll talk about that in one of the example problems. It's pretty important. And remember, those are going to be y values. Everything in this problem has to be y's because it's dy at the end. And x is going to be in terms of y. So it's going to be x equals what equation? So an example of this would be if y equals the square root of x, then our integral is going to be from a to b pi times y squared dy. And I'm sure right now you're thinking, wow, how did he get that? Well, go over to the function that we have and solve it for x. So we're going to we have the square root of x equals y, so we're going to square both sides. The square and the square root cancel out, and we get x equals y squared. So it's the same equation, it's just been written as an x equals problem instead of a y equals problem. Alright, so I went through this kind of quick. Again, I hope that you're going back and re-listening to things and trying to get this figured out a little bit more. But let's try an example here. Okay. And so what we're going to do is we're going to find the volume if y equals 1/2 x plus 1 is rotated around the x-axis. And so what we're going to do is we're going to consider what we refer to as a truncated cone. A truncated cone is one that has had its top chopped off. And so we're going to consider that cone from x equals 0 to x equals 4. And so I'm giving you the limits of our problem. So just like before, we're going to make sure we graph this first. So what you're going to do is you're going to graph that line. So we're going to go up 1, and then from here up 1 over 2. We're going to graph that line. Now we're going to spin that around the x-axis. That's the truncated cone that we're going to find the volume of. So I'm going to go from 4 to 0. and it's going to be pi times, remember, it's my y function I'm plugging in, so 1/2 x plus 1 squared dx. Again, I'm going to make sure I do this, everything in terms of x in this problem, because I'm spinning it around the x-axis. Just remember that, around the x-axis. Everything is in x. So there's two methods we can do for this problem. First method I'm going to go through is a substitution problem. So we're going to go u substitution like we did back a few sections ago. And what makes this problem hard, obviously, is the 1/2 x plus 1. So we're going to let u equal that. We're going to find the derivative of u with respect to x, and that would be 1/2. Do a cross multiply and solving that, we get dx equals 2 du. Rewrite my integral. Remember, you got to change your x values. So I plug the 4 and the 0 into the function and end up with 3 and 1. Again, if you need to stop and look at that, go ahead. And now that's a much easier function to integrate now. So I integrate that, add 1 to my exponent, and divide by that exponent. And by the way, I did forget that 2 when I rewrote that integral. That's where the 2 came from. So that's what's missing there. And so when I get for an answer for that, I get 52 pi over 3 units cubed. That's the volume of the truncated cone. Second method would be to just multiply it out, not to do a substitution. Sometimes it's not hard to do that if the thing that you're squaring in parentheses is not overly complicated. This one's not bad. You know, you do have a fraction there you got to square, but that's what you would have if you squared that, and then you would want to distribute your pi through each of those terms. And then you could go ahead and integrate that now. So add 1 to the squared and divide by that. I get pi x to the third over 12 plus pi x squared over 2 plus pi over x. Plus pi x. I'm going to integrate that from 4 to 0. And when you plug those numbers in, you would see that you'd still get 52 pi over 3 units cubed. It's up to you which way you want to do it. I don't care. Whatever way makes you happy. And so you don't have to go the same way every time. You can go back and forth on whatever way seems easier for you for that particular problem. Alright, let's try another example. At any point you want to stop these and try them on your own, by all means go ahead. Or if you just want to continue to go through and watch me do it and stop and go back and listen to it again, that's fine too. So now we're going to find the volume of the solid generated by rotating 2x plus 3y equals 6, y equals 0, which is the x-axis, and x equals 0, which is the y-axis, all around the x-axis. So I'm giving you 3 boundaries here. I'm giving you 3 functions, 3 curves, if you will, that act as boundaries for our area that we're going to spin. And so what I've done is I have solved the original function for y, because that's the main function that I'm spinning here. Alright, I'm spinning that line, and there's my x equals 0 and my y equals 0 lines, and I'm spinning those around the x-axis. So since it's around the x-axis, everything in this problem is in terms of x. Now what you notice is missing right now are my limits. I need to find those. So I need to find those intersections right now. Obviously the cone starts at 0, and then I can figure out where that root is on my calculator, or setting it equal to 0, setting your y equal to 0, whatever you want to do there, and figure out that that's x equals 3. So there are my limits, and now I'm going to treat this problem just like I did the last one. And once you get to this point, you might as well use your calculator for this. Just make sure you put it into your calculator correct. If you want to do the work by hand, practice that a little bit more, you're more than welcome to. Or you can let your calculator work, do the work for you. Again, be prepared on a quiz to be able to do both, one by hand maybe and one with your calculator. When you're all done, you should get an answer of 4 pi units cubed. If you can't get that, you should go back and look and make sure you put things in correctly or that you did the work right, depending on what you did. Now, what if we do the same exact problem now, but instead of spinning it around the x-axis, we spin it around the y-axis? So I take the same area, that same region, and spin it the opposite way. So we're spinning it, if you will, horizontally. Remember, the big difference in the problem when I spin it this way is that since I'm spinning it around the y-axis, everything in my problem has to be in terms of y. Everything has to be in terms of y. So it's a different shape. It's a different size. You're very likely to get a different answer when you do this. So remember, everything is in terms of y, and that means on my graph right now, I have to go from there to there. So obviously it goes to 0 again, it goes down to 0, but now I got to figure out where that y-intercept is, and that y-intercept is 3. So it goes from 0 up to 3. Actually, that should be 2. I think there's a mistake there. Should be 2. Yeah, that's not 3. It should be 2. You can tell from the earlier equation we had that it's going to be 2. So it goes from 0 to 2, and now I've rewritten that equation. I solved it for x instead of solving it for y, and that's my new function. Everything else is exactly the same. You can plug that in, and you can use your calculator even to do that, but you just have to make sure that you just put x's in the problem instead of y's, and it will work out the same way. Okay? And when you're all done, you should get an answer of 6 pi. Again, if you want to try that, go back and try that and see if you can do that correctly. Alright, so if you haven't done any practice yet, you certainly should do some now. I've done quite a few of these problems here for you, so I need you to try some and make sure you know how to do them on your own here before you get to the example problems. So I have 2 for you, 2 examples here. Again, after you see them written down here on the video, push pause, take some time, make sure you know how to set the problem up. I'll give you the integral after you've had a chance to think about it. I'll give you the integral, and then I'll give you the answer, and you can compare and see if you did it right. So for the first one, we're going to find the volume of the solid generated by rotating the region bounded by y equals x squared, y equals 2, and the y-axis around the y-axis. And the second question, we're going to find the volume of the solid generated by rotating y equals 2x plus 1, the x-axis, the y-axis, and x equals 3. So remember, x equals 3 is a vertical line around the x-axis. So remember, if we're rotating it around the y-axis, everything has to be in terms of y. If we're rotating it around the x-axis, everything has to be in terms of x. Okay? So go ahead and work on those. Alright, so just a little help here. Hopefully this is the integral you had for the first one. Your integral should have went from 2 to 0. Or from 0 to 2, excuse me. The function should have been pi times y dy, and that would give you a volume of that problem. It's like a bowl of 2 pi units cubed. From question number 2, your integral should have been from 0 to 3 pi times, in parentheses, 2x plus 1 quantity squared dx And your volume of that truncated cone should have been 57 pi. Alright, now that you're done with this, I'm going to give you, go back to Skyward, and you will be able to open up a PDF of some practice problems. We'll definitely talk about those in class tomorrow.